And the title of the talk is Data Maps for Data Exploration by Leland, McInnes. A little bit intro about Leland. Leland is a senior researcher at Tata Institute for Mathematics and Computing. He works to develop open source tools for data science, including UMap for dimension reduction, HDBScan for clustering, and PyNN descent for approximate nearest neighbor research. Please welcome him for his talk.
Mic on? Yes. Okay. Thank you very much. Thanks, Vincent, for the introduction. I'm going to be talking about data maps for data exploration. This is joint work with a bunch of my colleagues at the Tata Institute, John Healy, Colin Weir, B.Y. Hamlin. And before I start, I just want to explain this is framing for a big picture view. So I'm going to sort of provide big outlines for a 50,000-foot view of how I want to do things and more pique your interest. I'm going to give some examples, but I'm not going to get into details of all the nitty-gritty things. But first, I want to carefully delineate 3 different modes of doing data analysis that I'm going to refer to as query, search, and explore. And each mode is going to have an important place in data analysis, but some modes are currently far better served than others. So to explain the modes by analogy, I want you to imagine you've just arrived at a vast library you don't know anything about. If you know exactly what you're looking for, which book you want, you can just go and ask the librarian, and if they have it, they'll give you that book. So this is the query mode, where you know what you're looking for, you query for it exactly. But sometimes one doesn't always know exactly the right book. You know the subject area generally, and if you have a good librarian, you can go and ask that librarian, they'll direct you to the right set of shelves, and you can browse through the small set of books that are on those shelves and find the kind of thing you want. And this is what I'm going to refer to as search as opposed to query. You're not querying a specific thing, you're searching generally for the right section or right areas to look. The last case is sometimes you don't really know what you're even looking for. You just want to explore the library and find what's in it. There could be all kinds of interesting things you didn't know you were looking for before you started. And the way you want to do that, you just want to explore the library, ideally with a map with sections labeled, so you can figure out where to go to find the things that are in there, because you don't even know what the library has. All right, so let's talk about going from a query-based mode to a search-based mode. So this is the transition that's already underway in industry, and in practical terms, working with data sets is going to change from a query-based mode to more of a search-based mode when we're dealing with more and more of this unstructured data. So here's some pseudo SQL that might be a query you might have if you want to find movies like Casablanca. And the catch with this query mode is you have to know a lot of specifics. You have to know the internal structure of the database, what the fields are. You have to be able to pick everything out properly. Did you misspell any names? Did you guess the term that the database uses incorrectly? Did you include too many conditions and get nothing back? Did you include too few conditions and return the entire data table? Did you accidentally do an outer join? In contrast, what you'd like to be able to do is just what Google does, right? Just search movies like Casablanca. And this is what Google returns for you, and it's pretty good, actually. It's a pretty reasonable selection. So the question is, how does Google do things like this? And the answer is vector databases, also referred to as semantic search or a neural search engine. There are a bunch of different names for this, but it's really all the same thing. And this is the sort of thing that Google uses for its recommendations like this, or image search or video search. Lots of companies are doing this sort of thing. And in fact, vector databases are all the rage right now. Here's a bunch of different startups that I happen to have run into that are offering vector database solutions. So what is a vector database solution? Well, what makes up a vector database is 2 things. 1, turning your data into vectors, and 2, being able to search through those vectors very, very efficiently. And behind that, turning data into vectors, well, if you look at Hugging Face or OpenAI or Google or Facebook, turn out all kinds of huge neural network models that turn all kinds of things into embedding vectors. There's so many different ways to do this, it doesn't really deserve to be spoken to in any more detail. For fast vector search, there are actually a lot of different algorithms and implementations that will search through giant databases of vectors for the nearest neighbors of a vector very, very efficiently. There's solutions from Google, from Facebook, from Microsoft, from Spotify, and many, many others. Okay, so what we have to imagine is if you wanted to convert a whole bunch of documents into vectors, how would you do it? Well, you could start with Word to Vec and just average word vectors for the document. That's good enough for short documents, but you could use Universal Sentence Encoder, that works too. Or Sentence BERT, that would be even better probably. If you have a big pile of images, you could use an image-based neural network. That gives embeddings. There are many choices. You could use your favorite, ResNet 50 might be good. If you have a mixture of documents and images, OpenAI Clip actually embeds text and images into the same space. You can work with mixtures of the two. And the short answer really is that in this day and age, if you're working with piles of documents, images, audio, video, all that, there's already a pre-trained model that embeds this into a vector space for you. And if you have more specific data, well, you can always fine-tune those models, or if you have really specific data, you can even build your own models yourself. And it's almost certain that there's a fast vector search technique that's going to suit you. In the background of that screenshot is from A&N benchmarks. There are so many different approximate nearest neighbor search implementations out there that the plots just look crazy now. There's going to be something that works for you. So this is covered. And the reason for this is that this technology powers all kinds of different things, from semantic search to query expansion to fuzzy matching, reverse image search, recommendation systems, anomaly detection, deduplication. This combination of powerful vector representations and fast vector search is rapidly becoming foundational for a foundational technology for all sorts of data work. And there's another interesting thing that's a little more subtle for vector databases that I really like. It kind of acts like API encapsulation for data. You can package up a complex data set using vector embeddings, encoding your domain knowledge into the notion of similarity or distance between those vectors. And now, anyone who wants to use your database doesn't need to know anything about how the internals of your database works. They just need to be able to say, I want to find things like this, and that's all. And better yet, if your internal data changes, where what you would have been doing previously is adding extra columns to your database tables, people aren't going to know about that. It doesn't matter, because you just encode all that new extra data you have into a new vector representation, publish it, and as far as the end users using that data are concerned, they're just saying, find me things like this, nothing changes. They automatically get all the benefits of that extra data without having to know anything about the data. So the internal schemas, the internal details don't need to matter anymore. Okay, so hopefully I've convinced you that this search mode powered by vector databases is both powerful and fundamental. But now I want to convince you that there's one more step that we'd like to take that can provide really powerful tools for data analysis and allow you to explore data in a much richer way. So it turns out that we're visual animals, and there's nothing like looking for finding things. And especially if you want to find things you didn't even know you were looking for, a visual representation is going to be the best way to do it. What we want is that big picture, 50,000 foot view of everything, so you can start from there and then work your way down to find the things that are of interest to you. And our solution to that is interactive data maps. What's that? Well, a data map is really just the application of a dimension reduction technique, taking a pile of high-dimensional vectors and reducing them down to 2 or 3 dimensions so that they can be visualized in a plot. So each point represents a vector from your original data, and you can see the structure and interrelationships between these data points. And recent advances in the last 2 decades or so have provided far more powerful manifold learning techniques that can do this and provide really rich representations even in 2 or 3D. The problem is, what does it really mean? If you're a data analyst and you just get a plot with a lot of dots on it, it doesn't really help you understand your data. Maybe you can see some interrelationships, but you need more than that. So, Google Maps is the gold standard for making data accessible and easy to use in map form. And so my claim is we need to learn some lessons from Google Maps to make our data maps more meaningful for a user. So what we want is our data maps to be as accessible and easy to use to interactively explore as Google Maps is. So let's go back and learn our lessons from Google Maps. First of all, there's down on the bottom right corner there that interesting little thing, and that allows you to choose a zoom level. And that matters a lot, because it means you can zoom all the way out and get the big picture view of countries and continents. You can zoom in and get state level information. You can zoom in further and see cities. Further still, you can get buildings, streets. And the key here is that the level of detail that you need for your task at hand can vary. And you need to be able to smoothly move from one to the next to find whatever is going to suit your task. But let's take a moment and go back out to that state, city level view that we had. There's something else important going on here. And that's these labels. These provide you a way to orient yourself of what's going on in this map. If we took those away, I think people might actually struggle to guess where in the world we were looking at. But as soon as those labels go there, you know what you're looking at, you can orient yourself, you can figure out where to go, where you want to zoom in on. So labels like that are going to be extremely helpful. Google also provides hopper interactions. You can hover over any interesting data points. It'll just show you information about that data point. So you can quickly scan over a bunch of locations, find what's interesting. And when you click on it, it brings up a much more detailed report so you can look into the details of it. Being able to easily access a lot more detail really matters to the user experience. And of course, it's Google, so we can search. And a textual search lets the user quickly find potential items of interest. But it's more than that. By showing the search on the map, they get to see clusters and outliers, either of which might be important for what they're doing. A less well-known but very useful feature is layers. So you could turn on different layers in a Google map and add extra data. So here I turned on layers for the relief map showing elevation and bike paths. So if I was trying to bike around Seattle, this is information I would really, really want. I like to be able to layer that onto the map depending on what kinds of information one needs. So we need to make data maps as navigable and easy to use as this. So how do we build a rich interactive data map that an analyst can explore like a Google Maps view of their data set? There's a pipeline that we need to construct to really make this all work. Now, the first two portions of this pipeline, data to vectors and fast vector search, that's really what vector databases are all about. Turning those vectors into maps, there's a bunch of manifold learning techniques. We can do that reasonably. The map annotation is harder, and the interactive visualization is largely something you usually just have to build yourself from the ground up, which is fine, but it's a lot of work. So before I go on, I want to highlight our contributions because at the Tubbs Institute, we've been working on a variety of tools and projects that can be pieced together into a coherent approach to do various parts of this whole tool chain. And I should note, all of this is open source. It's all on GitHub. It's all on PyData. You can go and grab any of it and work with it. So Vectorizers is our set of tools for vectorizing data. Now, we're a small research institute in Canada. We aren't going to compete with Facebook, Google, and OpenAI at training giant neural networks. We don't have the data sets or the compute to manage to do that. So we're actually interested in how to vectorize all sorts of other kinds of data. The small data, idiomatic corpuses. We work with cyber defense in Canada, the Canadian government. So IP traffic flows, event logs, malware binaries. Being able to vectorize all kinds of different kinds of data is what this sort of tooling is built around. We needed fast vector search. We built our own method for this that solved our problems. It works with a lot of different distance functions and a lot of flexibility for things that we need. In practice, it turns out it's actually very fast and competitive with the solutions from Google, Facebook, and Microsoft. We also built the UMAP library for manifold learning. It's become one of the go-to methods for this data map style approach. On the right there's a couple of websites that actually make use of UMAP embeddings for interactive views of either textbooks, academic textbooks, or actually just non-fiction books. Sorry, fiction books. And you can explore those, and it's a really fun way to explore and look at things. Quite some time ago, we built a fast scalable version of HDB scan clustering, and that algorithm has proved to be a crucial part in providing those textual annotation labels, and at the varying levels of detail we need for these data maps. So in essence, we're using HDB scan and hierarchical clustering and density-based clustering to find the equivalent of countries, states, cities, suburbs, streets in their data maps, starting from just the data. And lastly, we're working on TNT, which is our effort to put together a library designed to make it easy for you to build an interactive data map, either in a notebook or as a web application. And this is the newest of our projects. It's developing very, very rapidly, but it's ready for basic use now, and hopefully we'd love to have you try it out and see how it goes. So I should note, it's built on top of the panel library from Anaconda, so it really just provides a bunch of panes and widgets that are pre-built for the needs of building interactive data map tools. And you can take that as a big bucket of Lego and glue it together in whatever construction you need very quickly. So our goal here is not to provide some very polished final product that is fixed in stone, but rather a whole bunch of tools that you can get an 80% solution for your very specific problem put together very quickly. All right, so that was some of the technology. What can we actually build with all of this? So I want to provide an example. I picked an example data set of the COVID-19 data. It is a collection of tens of thousands, in fact almost 1 million now, research papers that are related to COVID-19 in some way. It's a lot of material to sort through, that's a lot of documents. How does one explore a data set that large? Well, fortunately for us, the COVID-19 dataset comes with its own vector representation of the papers that was using a different deep learning-based approach that actually is specifically designed for scientific documents. It cares about citation information and so on. This is great. We're just going to use that out of the box. And that means we can apply UMAP directly to those embeddings of the documents to get our basic map for where we want to go. And then we can use TNT to explore the results. For the purposes of this demo, I'm downsampling to 100,000 papers. That's more than enough to provide a vast corpus to sift through. So TNT makes making an interactive map straightforward. This is the minimum you would need to just get going. You hand it the data map, and in this case I handed it some hovertext data as well. And what you get out is something like this. The large cluster at the bottom left there is just short articles, reviews, commentary, and stuff like that. So let's just ignore that for a moment. There's some interesting structure going on here in the main cluster. So what's going on there? Well, it's an interactive map. We can zoom in easily. And you can hover over the things and get hover text. And you see that, well, there's something about surgery-related things there, maybe? Okay. We can inject more information into this pretty easily to make the map more comprehensible. So TNT is designed to make all this stuff pretty easy. We want you to provide as little information as possible, and then we're opinionated about the results so that you get something that should work reasonably well. So we can specify some labeling by the primary field of research of the paper, and I'm going to do marker size based on the citation count, so that less cited papers kind of fade further into the background. What we get out is something looking a bit like that, and that can tell us a lot at a high level. Most of the papers are from the field of medicine, which is exactly what you'd expect, but there are some notable exceptions, and there's a surprisingly diverse range of fields. If we look at that area that we zoomed in on before, we can zoom in on that again, and we see there's a bunch of different fields there, and several clusters have incredibly distinct primary fields. So the surgical cluster, as one might expect, is all about medicine, but there's this cluster down here that's all computer science and mathematics, not necessarily what one would have expected to find when we were looking through COVID-19 papers. And there's also this other cluster here where the predominant field is probably environmental science. So right away, just from having this as a map to look through, we've already found interesting things to explore further. Stepping back from that, there's a lot of papers here that are, well, a lot of separate cluster, have a surprisingly large range of different fields of study. So let's zoom in there. There aren't distinct clusters purely in points, but there's clusters in the fields of study. There's this group, which is largely papers from business and economics, and then another small group here that's a different environmental science cluster. So there's something interesting going on there. To make this easier to navigate and make more sense of, we can use a bunch of tooling from our vectorizers library to actually generate a shared Word document space with the Spectre document vectors. We can then use HTTP-scan and PyData to cluster the papers and find nearby words to those cluster centers. If you're familiar with the top-to-vec topic modeling algorithm, this is basically doing exactly the same thing. And all of that work actually turns out to be very easy in TNT. We've automated most of that away for you because this is the sort of thing you're going to want to be doing a lot. And so this is more of an eye chart. I'm not expecting you to read the code in detail, but more see that it's still not a whole lot of code, and you can get a result more like this, where now we have high-level labels that we can look at, help guide what we're looking at. So let's zoom into that region again. You can see the surgery cluster gets keywords like underwent, millimeters, ectomy. This is obviously surgery related. And in the environmental science cluster, you've got -95, that's obviously from N95, worn and airborne, so this is probably about masking or air quality, things like that. If we actually zoom in further, more detailed labels reveal themselves, and we can see that computer science cluster is actually about clearly deep learning, and if you mouse over that, that's all about deep learning for chest x-rays. There's SEIR modeling in the bottom right. And then there's a group with IoT, Bluetooth, and things. That's from Internet of Things. And that's actually all about Bluetooth and IoT devices being used for COVID tracking apps. So you can find all the papers about that pretty quickly. If we zoom in on that environmental science cluster, we get more detailed labeling. It makes it clear what topics are covered there. It's all about airflow, aerosols, indoor respirators, masks, all the things you would expect to be in there somewhere, and obviously there are a whole bunch of environmental science papers about that. We can explore some of those other areas of interest. Here we see some of the overlapping layers of labeling with the economics splitting out about concern about markets in the face of COVID, and managerial and organizational changes that were wrought by COVID from remote work policies. We can also see those papers clustering stress and anxiety, from the psychology field, as well as a cluster down at the bottom that's all about education, probably remote learning. Zooming in further, we can see further delineations in the economics papers, and that environmental science cluster that we didn't really understand has passenger transportation bus. It's obviously about all the changes to things like air quality when there were sudden drops in the amount of travel and transport during COVID. So with just a little work, we have tools that allow us to quickly and easily navigate the vast and diverse corpus that we had there. Makes it easier to find things of interest. But TNT allows us to add other ways to interact with the data as well. So this time, this is an eye chart. I'm not expecting you to read this. I'm putting this here so you can see this is the total amount of code required. It's not a whole lot. And the thing here is that we're putting in a whole bunch of different extra building blocks that can add information for being able to search, add information panes, control panes to layer different data over the plot, and link them all together easily. So what we get is something a bit like this. You can serve it up as a web app from the command line, or you can view it natively in a notebook. It doesn't matter. This is one of the beauties of Panel. It lets you do either or. And if you click on an individual point, it'll bring up all the details about the paper, including a link to the actual paper itself, so you can go and read it. We also have a search pane. You can search for whatever you want, just strings in the data, and you can tie this search to whatever metadata you want. It doesn't need to be anything specific. It just needs to align row for row with the data that is being plotted. And so you can immediately see two clusters related to vaccines. One cluster is all about vaccine hesitancy, and the other cluster is in the biology field, and that's obviously all about vaccine development. We have plot controls. You can change what you're coloring by. Let's color by influential citations and see which things are more influential. You can change the hover text column to the TLDR of the paper and get, instead of titles of the papers, quick summaries of the papers. All these things are easy to put together and link together as you need. And there's still a whole lot more tooling available in TNT. Here's a preview of some of the stuff that's on the bleeding edge, as well as a bunch of upcoming features. So in this case, I've got an updated version of the core data set where I eliminated anything with an abstract that was too short and removed the low citation counts, so we get a slightly different map. But and note that we're actually serving this as a web app via panel. So we can have things like a data table that changes. If we select points, it'll only show in that data table the selected points of the cluster or region that you selected. So you can interactively pick out regions in the plot and find out more about it. Note also that there's a new label button in the bottom right, and that's a label editor. We can actually select points, assign them a new tag or label, and it'll store that information off. You can save it back and label the data yourself. So you could actually use TNT to quickly build a labeling tool if that's what you want to do. The options are pretty unlimited. So we've actually got several different ways you can do search. You can do a keyword-based search that actually can handle longer text a lot more easily. We have semantic search using effectively a vector database, backing it all, whatever you want to do. And that's all just built in. It's just throw in a line, say, I want a semantic search widget here. We're also busy building out a variety of summarizing tools. So if you select data, you can get a summary of the selection. So note at the very bottom there, there's a distinct cluster that's in blue, that's CS papers. What's that all about? Well, if you select just those, we get a word cloud summary. It's all about the things you would expect. And we have a summary of the value counts of the different fields in that cluster or that selection. So it's really easy to build your own summarizers. We are building up a set of different ones, things like feature importance plots and anything you can think of. It's actually pretty easy to make your own. All you have to be able to do is take an input of data and output either a data frame or a plot or some HTML, whatever you need. And lastly, we're actually looking at using large language models to generate labels of those clusters. Instead of using those sort of keyword descriptions, which are indicative of what's going on, you can actually hand a lot of the information to a large language model and get really readable results. So rather than things relating to surgery, we get medical surgical procedures and much more detailed labeling. It adapts to different kinds of topics very well and provides an efficient overview of the content. You get things like air quality impacts of COVID-19 lockdowns. That's a much better description of that region of the data set. And it provides good specificity when you zoom in as well. There's a lot of detail in those specific labels. So, to wrap up, what do I want you to take away from this talk? I want you to take away that vector databases are the future, and you should probably get on board now, and we're going to end up with a lot of vector databases squirreled away in organizations all over the place in our future. And interactive data maps are a great way to be able to understand and explore a vector database in a holistic way. So I want you to think about this as exploratory data analysis for big unstructured data, or exploratory data analysis for the 21st century, when we're not dealing with nice, simple tabular data where we can do statistical standard exploratory data analysis. Now we've got big, messy, unstructured data. How do we look at that? How do we explore that? Finally, TNT, our library, is a powerful way to quickly put together an 80% solution with interactive data maps and different tools that are custom to your needs. So we're not providing an end-to-end solution, we're providing you with the tools you need to build whatever it is you want to build. Now, all of this and more can be found on GitHub. We'd love to collaborate and expand what these kinds of tools can do. So, by all means, come talk to us. You can find us on GitHub. Thank you. Yes, at the back.
Yeah, this is really cool. The higher level clustering label is really interesting, and I could see how that works when we're dealing with embeddings of text data. I'm wondering, does this work for situations where the underlying things we're making embeddings for is not text, and like it can maybe make these higher level clusters with dummy text that a subject matter expert can later come and label after the fact, or is that part of what's working?
So, let me make sure I understand your question. It's that with text data, the high level labeling looks kind of good,
yeah.
But can we handle other sorts of data?
Yeah.
And so the answer to that is yes. The labeling I showed there was a joint vector space labeling technique, but we actually have a bunch of different ways of generating labels based on tabular data. We can do feature importance-based labeling of clusters for what makes this cluster distinct from the others. We can work with sparse data. We even got random sampling-based labelers. We can label with, this is upcoming, I've got prototypes to do it, label with images rather than text. So if you have a giant pile of image data and you want some labels, you can have like example images hovering over the clusters, and they'll change as you zoom in or out. So yes, we can handle more than just text, and we would love to be able to handle even more. I think it's not so bad to add even more different ways of generating these sorts of labels. So if you have more ideas about what you need, please, let's talk. Yes?
Thanks so much. Kind of like two questions. One, I've been playing with this kind of stuff before, and two bottlenecks for me were one, dimensionality reduction between the very large data sets, like all in RAM or how or where, going from 768 dimensions to 2. And then the other was the hyperparameter tuning in the HD scan. Sometimes you need like one layer more and the whole thing explodes into a million clusters. And 1 million, so like how do you handle it here once kind of building these file systems?
So the first question was about UMAP. Was that about scaling to really, really large data sets? The answer to that, I would check out the Rapids, NVIDIA Rapids implementation of UMAP, which runs on GPUs. And that will run very fast for very large data sets. I believe they have multi-GPU solutions for that as well, so you can even scale it out to won't fit on a single GPU's RAM. So that would be the solution to that. The second question was about HTTP scan for the clustering, and it's tricky sometimes to get the parameters right. So we actually developed a slightly different approach. We're using HTTP scan, but we've got some tricks built in here to actually do the clustering a lot more slickly and avoid a lot of those problems. So really, to build up the hierarchy, it's a lot slicker than you might think, and not very hard to choose parameters surprisingly well. So we have solutions for that problem. We're very familiar with the internals of HTTP scan, so we can mess with things. Yes?
Do you have any thoughts on, if you're working with data that doesn't fall completely into these traditional categories, how you would generate vector embeddings for EKG data of the heart or something that's kind of unusual?
Yeah, okay, so the question is, how do you generate vector embeddings for things that are more unusual data? So your example was EKG heart data. Actually, a sliding window embedding based technique can work surprisingly well, depending on what you're trying to get out of that data. The short answer is vectorizing data is kind of down to what your end task with it is. And I think that's a matter of you having the domain expertise about that data to work out the best way to turn it into vectors. Our vectorizers package has a wide range of different techniques for working with variable length sequence data, is how I would describe it. And it might have a solution that might work for you, but in general, that's a challenging problem, but I think it's a problem that more and more people are going to try and solve. So hopefully, either there's already a solution for you, or there's probably one coming, if your data is popular enough. Is that close enough to what you were looking for?
If it's not popular enough, where would you go?
So if it's not popular enough, I would look at our vectorizers package, because we actually really care about data that's not having lots of neural networks built for it. We're not building neural network techniques. We're building a lot more just standard ML techniques for dealing with those sorts of data. And come talk to us. We can try and figure out if maybe there's a solution for you. Yes, at the back.
And piggybacking off of that, what about language? I know language data is really popular, hence natural language processing. But what we do, but this has to do more with transfer learning, embeddings for transfer learning versus task-specific ones. Like, would you say that transfer learning embeddings tend to be really huge because you're trying to throw everything out of the kitchen sink, or and that's why?
Sorry, I'm not quite getting the question.
Like, are embeddings? Would you say that embeddings for transfer learning type tasks are going to be bigger?
As in more prevalent?
Yeah.
Yeah, I expect they'll get used, because even if they're not ideal, they're probably good enough for a number of tasks. And being good enough might be sufficient. Having a fine-tuned model that's more specific to your needs.
Not necessarily for, not necessarily in terms of prevalence, but in terms of, because I want to be able to make the embeddings compressible, if that makes sense, or kind of make them efficient, space efficient.
You mean the dimension of the embedding?
Yeah.
Okay, so the question is, are the transfer learning techniques going to produce higher dimensional embeddings generally?
Yes.
Quite possibly, and certainly the more that people are putting effort into these various neural embedding techniques, everything seems to be getting higher and higher dimensional. On the other hand, the popular manifold learning algorithms, TSNE, UMAP, things like that, actually do a surprisingly good job working with even those very high dimensional data sets, and still presenting a lot of really relevant structure in 2D or 3D representations. So you still end up with good looking maps out of it.
All right.
All right, I'm keeping everyone from lunch, so thank you very much.